This was originally meant to be a tutorial session, but due to some scheduling conflict, I'm now doing a PhD session, so I want to do a little bit of both. I kept some of the original slides about OpenStack and the TOSCA integration, and I want to show you also a little bit about my PhD topic, my research project, and how this integrates into the cloud stack here.
This is 15 minutes.
Yeah. Oh yeah. I should start. I gave you one time. It's okay. Yeah, I was here last year at the summer school and introduced my research project before, so maybe some of you remember this, and I can tell you a little bit about the progress and maybe what's happened since then. So this is the agenda for my talk. I want to first introduce you to my research project, which is about cloud security. So this is what the security aspects are about. And then the next three main topics here will be about the cloud stack which I'm using, which is built around OpenStack as a cloud provider on a special type of hardware that we use, and which is later integrated into TOSCA. And some of that you heard already on Monday from my colleague Uwe and Frank Leimann as well. And so maybe something will be familiar, and maybe I can give you a little bit more insight into how the cloud infrastructure actually works. So this is my research project, the Cicada project, security aspects for cloud deployment automation. It can be characterized by these 4 points basically. It's about providing security features for cloud services. And these security features can be integrated into cloud services, which are defined in a formal way with TOSCA automatically during the deployment or before the deployment, more or less. So basically my PhD work can be separated into 2 main parts. One of those is the creation of the security aspects. Some of them are like standalone features basically, which you can also use outside of any automation framework or any automated deployment system. And then the other big part is the integration into the cloud deployment automation and the automated integration into cloud service models in TOSCA. So this is basically the flow of things you have to do in order for this to work. You first have to create the security aspects, and then we have defined sort of a high-level policy language, which I presented here last year, that allows us to specify security requirements for cloud services, following the policy definitions in the TOSCA language, and this later allows a transformation of the cloud service to include the security features which have been selected by the policies. And these will then be active in the deployed instance of the cloud service. So this is the high-level architecture of my sort of framework. Today I'll be focusing on the cloud infrastructure, which you can see on the right here. This is where OpenStack and TOSCA comes in. The repository of security aspects is this first big part of my research work, which I mentioned, where the actual security aspects will be created. Last year I presented the first one of these aspects, which was a centralized key store for cloud services. So this allows us to store any kind of security relevant information, like proxy user credentials, logins to different systems in a centralized location, so that you don't have these distributed over a large infrastructure, but you can manage them from a central point and you can control access to those. Another addition to this, which I already mentioned last year, was a security monitoring system which manages the access to these security credentials. Another part which I'm currently working on, which I'm probably going to present at another conference soon, is hopefully is a file system adapter, which is also built on top of a service of OpenStack, which allows us to securely delete objects which have been stored there. So when you consider cloud storage systems, usually you consider the security why you want these objects to reside in the storage. You don't want anybody else to access those. You don't want them to get lost, but you usually don't consider what happens to those objects when you don't need them anymore. So the secure deletion of objects is something that is being researched in this current work. So let's go to the next part of the presentation. So if we want to deploy these software as a service offerings, these software applications in the cloud, basically we have requirements depending on what level of cloud service deployment we are on. We all know these different cloud service types. So if you want to deploy infrastructure as a service components, of course you have to manage the physical infrastructure. If you want to offer platform components, you have to manage the instances of these services. You have to create users, you have to scale these services, you have to do maintenance to keep them running. For software as a service, you have to care about complex software topologies, which is where TOSCA comes in. You have to provision new instances. So since we learned yesterday that cloud applications are composite applications, these are built from different individual components. So when you have these different cloud service levels, software, platform and infrastructure as a service, you can build a higher level applications on top of the lower level applications, which is why when we deploy cloud services with TOSCA, we usually use some infrastructure provider beneath to provide virtual machines. We use platform providers to provide higher level functionality like databases as a service, message queues and things like those. So the goal in the context of my research project is to deploy secure applications. So a requirement for this is to have these components available as services, which is why I decided to use OpenStack in my work, because it not only provides infrastructure services but also platform services like the object store, which I mentioned later. So in this chapter I want to give you an overview over the components in OpenStack and what their actual functionality is and how they integrate with each other. Since we heard a lot about cloud infrastructures on Monday and OpenStack was mentioned a lot, I thought it would be interesting to get a closer look at how this framework actually works, what the individual components are, what their tasks are, how they interact with each other. This is always a good slide to introduce the system because it shows all the core components which are necessary, and it can give you an idea what the system actually does. So the main component which is usually used is the compute component in the middle, which provisions the actual virtual machines. It manages the hypervisors and allows you to provision instances of virtual machine images. It allows you to do snapshots, to migrate these to other hypervisor hosts. So this is basically a controller component for virtual machines, for hypervisors. Then you have an image repository which stores these images. You have the object store, which you can use as a platform component, sort of. The dashboard on top is basically a user interface for all these components. It uses the same API as all the rest of the system. The networking component, which is mentioned here, is Neutron or Quantum, which it was called earlier. Like Breiter mentioned on Monday already, it's not sure how this project is going to continue. In the Nova component, the compute component, there is another networking component, which was the first one that the project had. It's the one I'm currently using as well. The Neutron component, it lacks good documentation. It's very hard to configure because there's a very quick development and you don't have any documentation. You don't really have automated setup tools. So it's not used a lot currently. I'm going to show you some more features of these individual components in the next slides. But first I want to tell you a little bit about the core concepts of OpenStack. So as you've seen already, it's separated into components which are loosely coupled in a way. Some providers which use OpenStack themselves, IBM is one example of those. They replace some of these components with their own implementations. They enhance the functionality. These components are all separate from each other, so they share no common backend systems. They have no data stored in the back, which is common to all of those. They can all be separated, so you can distribute them arbitrarily over an infrastructure of any size, which allows you to scale exactly the components that you need in your case, depending on which you need the most performance at. They all interact using a versioned API, so this allows you to run multiple versions of the same component in one installation, and also allows you to upgrade components independently of each other. You don't need to update to a new version of the entire system. You can do this with individual components, and they will be able to use special API endpoints which indicate that the API should use an indicated version. All the calls that you do over the API require authentication, and this is where the centralized authentication component comes in, which we'll see very soon. One very important factor when you consider using the system is that there is no built-in high availability or redundancy mechanism.
For the system itself?
For the system itself, right, and also for the resources that have been provisioned by the system.
Although you can define high availability policies?
You can define policies, but that requires the underlying providers. So this only works if you use providers of resources that are not done by OpenStack itself. So for example, for storage, this is the case. Then OpenStack will select a storage provider which has high availability. This is also an important aspect. A lot of the components in OpenStack can do the functionality themselves, more or less, or they can bypass these requests to another provider. We'll see this later in the storage component especially. So the key component basically which you will always need is this keystone authentication component. Since all the API requests need authentication and OpenStack uses a distributed or a federated authentication system, there is always a centralized, or it can be federated to multiple instances, authentication system, so that the individual service components of OpenStack don't need to authenticate requests themselves. This component here, Keystone, authenticates all the user requests and hands out a token which signifies a valid authenticated user, and the individual services can then validate this token in Keystone and will then process the request. Keystone is also responsible for managing the API endpoints of all the other components. So whenever a service component is introduced into your OpenStack cluster, it needs to register its API endpoint at Keystone so that Keystone can recognize authenticate or token validation requests by this component. And Keystone will also tell users which API endpoint to use for a certain service. So when I authenticate against Keystone, it can tell me what API endpoints I'm allowed to access. Another component which you will always need is the Glance image repository. This is the component which stores all the virtual machine images which are later used to spawn instances of virtual machines. This is where OpenStack is a little bit different than other cloud providers. It doesn't support creating new images. You maybe know this functionality from VMware or VirtualBox, S2 virtualization, or ESX provides this as well. You can create empty images and install something into them or copy something into this empty image. And this is the way that you usually use to create virtual machines. You start with an empty image, install something in there, and then you have your new instance image. You cannot do this with OpenStack. The functionality just isn't there. You always need an image which was pre-configured, which you can boot into. This is similar to what other cloud providers do. So here OpenStack is more like a cloud provider and not so much like a virtualization system. It's somewhere in between. So Amazon also does it this way, and Azure as well. You cannot create empty images there and install from bootable CDs or something like that. Glance supports multiple backends, so you don't always have to store the images in there. It's basically only a repository which links to some resources. It can store these resources locally, or it can reference external locations, so you can reference images on the web or somewhere else. The next two components I'm going to show you are storage components. These are very different from each other. So the first one here, the Cinder component, manages block storage. So this is basically something like hard disks. Block storage is different from the other storage options in that it's always a one-to-one association. You always have one block storage volume which is associated to one virtual machine. So you cannot use this component to do a shared storage, which is something that people are often confused about when cloud storage offerings like this are considered. this is one of the components which has a very tight integration with backend systems like storage area networks or other enterprise storage systems. But like the other components as well, Cinder can also manage the storage completely by itself. So when you do a basic setup, Cinder will require you to set up a Linux LVM physical volume or volume group basically on top of that, which Cinder then uses to create logical volumes based on the volumes that you want to use in your virtual machine. So when you create a volume of 1 GB to attach to a virtual machine, it will create this identical volume in the LVM system of Linux and then pass this on to the virtual machine. Here, OpenStack always uses iSCSI to do the forwarding of the actual disk access. If you use a storage area network instead of the local SUN, local LVM storage, Cinder doesn't really allocate any storage at all. It just relays the request to generate a new volume to the storage area network, and more importantly, it will also relay the request for disk access directly to the SUN component. So in this case, all your disk access requests don't go through the Cinder component anymore or through any of the OpenStack components, but Cinder will directly map the virtual machine to the storage area network. This also means that your network setup has to support this use case. The network setup will get pretty complicated if you want to support this, especially with storage area network technologies. But this will get you the highest performance of block storage because you don't go through any other software components. Virtual machines directly access the hardware storage area network. Another storage component which is very different is the Swift Object Store. So this is more of a platform as a service offering. It's not an infrastructure component where you have direct access to physical storage volume or something like that. It actually offers you, as the only component, this is basically built around reliability and high availability and also high performance in large environments. So the idea for this, it's an object store, so you can store objects in it, like with a key value database, you store an object, this is the value, you get a key, it's the reference which you can use to access the object. And Swift allows you to store these objects redundantly. It uses replication rings for this purpose, and each node in the replication ring stores the objects on its local disk. You can use replication policies to specify in which way the objects are replicated, how many replicas you want of each object, and they will then be distributed amongst the nodes in the ring. The access to these objects isn't going directly to the storage nodes, but through proxy nodes, and these can also be set up in a redundant way. They don't have to, you can also only use one of them. Storage nodes as well, you can only use one of them. But when you have multiple proxy nodes, they will select the storage node which hosts the actual object that you want, because due to the replication, it might not be available on all of the nodes. The storage nodes, they will replicate amongst each other. If one of them fails, they will enforce the storage policy by replicating the objects that they have to still have enough replicas. So this is different than the block storage. This is more of a platform as a service offering, which also isn't directly used by any of the OpenStack components itself. You can use it if you want to store the images of plants in it, but that's the only part where you can actually integrate this with other OpenStack services. So this is something that is directly being used by the application. And this is also where I'm currently integrating the secure deletion mechanism, which I mentioned in the beginning. Since the time is already over, I'm probably only going to cover this one as well. I prepared something for the integration in TOSCA, but I think this was already mentioned, probably to enough extent. So the core component, which is the most important one, is the NOVA component, which manages all the API requests which go to all the things that consider virtual machines. Usually when you use OpenStack, you don't communicate with any of the other components directly because they will all be accessed through NOVA, except the object store. Right? The object store is used by your application. The NOVA component itself can be split into more subcomponents which have individual functionalities. The most important ones are the NOVA scheduler and the NOVA compute component. The compute component is the one which actually controls the hypervisor, and the scheduler is the one which keeps track in a message queue of all the requests that you do to create virtual machines, destroy them, and it will then forward these to compute nodes as soon as they become available. I want to quickly show you the setup which we currently have so that you get an idea of how this looks in reality. It's a setup consisting of 7 nodes. The last nodes are all identical. The first 2 nodes have different functionalities. Node 1 here is a controller. It runs the scheduler, the Nova API. The nodes 2 through 7, they run the compute components, so they are only hypervisor hosts. Additional services here on Node 2 are the 2 storage services. So Node 2 has an hypervisor and storage. Node 1 is the controller which runs all the other services that you need, like the Nova networking, the user interface, image repository, authentication mechanism. This then means that the setup of the network, for example, has to be adjusted to this. So if the network component runs on Node 1, this needs internet access. All the other components are in an internal network, communicate through each other, and all the requests that go to the outside go through the controller node. So this is the setup we have, and you can see that Node 2 is a little bit different than the others that run hypervisor hosts. So this means you can separate them into availability zones. This is probably the last feature which I'm going to be able to mention today. Yeah. Okay, so
the summary would be very nice.
Okay, the summary. Summary would be that OpenStack features functionalities which can be used in infrastructure as a service environments, also as platform services. And if you use it as a provider for your cloud environment, slide which I wasn't able to show, you can use the API to integrate it with automation frameworks like TOSCA, where a lot of work is going on currently. And if you do research in cloud-related technologies, it's a great technology because you can work with all the components since they're open source and run on your own hardware. You're not bound to a cloud provider where you only have access to the API and never can manipulate the underlying infrastructure. Okay. Thank you.
One question. I'd like to thank you very much to get me earlier to the beer. Yeah, thank you very much.